All right, 7.3, number 13. First of all, did you guys see the remind I sent out? My answer for B was wrong. I'm not sure what I did. It was supposed to be 23.1 meters a second instead of 30 or whatever it was on it. Okay, so sorry about that. Okay, so here we go. So Sonic the Hedgehog is going down a ski jump. He can be treated as a solid sphere, blah, 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 blah. All right, and then you're given this drawing. All right, so all right, and so there are 3 points that we sort of care about, right? There's this point up here, which I am going to call point capital A. There's this point down here, which I'm going to call point B. And there's this point down here, which I'm going to call point C. Okay? The problem tells us that, once again, Sonic can be treated as a solid sphere. I, for a solid sphere, is 2/5 of mr squared. Again, because this is all about conservation of energy, all that we really care about is this, and it is important because it tells us the value of that fraction b. Cool? This b and that b have no correlation. All right, everybody good? Okay. All right, so what we're trying to find in the first question is what the velocity is at point B. So question A. We're trying to find this velocity here. Yes? All right, so let's start by writing down what we know. So at point A, I know his height. All right, so this one has got another one of these weird convoluted drawings. I'm trying to give you guys more exposure to these because I remember this was on that last test. This was something that you guys struggled with. So what should I use for the height up there at point A? Can I use the 27 meters? What should I use? So remember, my strong recommendation to you guys, and there are other ways of doing it, but my strong recommendation for you is to choose the lowest point to be a height of 0, and then measure everything up from there. Okay? And if we do that, that means that at point B, our height is 8 meters, and our height at point A is 35 meters, right? Because the 8 plus the 27 on the drawing. Follow? All right? And it tells you he starts from rest, so the velocity at point A is 0. Okay? So that's kind of our given information. Question A wants to know the velocity at point B, and then question B wants to know the velocity at point C. All right, so any problems with sort of given information? Okay, so first of all, are we all cool with the fact that this is a conservation of energy problem? It's a rolling thing. There are no non-conservative forces doing work, so our total energy is going to be constant the entire time he's rolling and as he's flying through the air at the end. Cool? All right, so to solve part A, we're going to go, oh, well, the total energy at point A has got to equal the total energy at point B, right? Okay, so at point A, what types of energy do we have, you guys? Just GPE, right? Doesn't he start at rest? Am I remembering right? Yeah? Okay. So that means that the GPE at point A has got to equal, let's see, at point B, we've still got GPE because the height isn't 0 anymore. Plus, there's going to be kinetic energy because he's moving. And there's rotational kinetic energy because he's rolling. He's rotating, right? Any problems there? Okay, so let's plug in our numbers. So the GPE at A, that should be his mass times 9.8 times the height. So that's A. At B, his GPE is mass times 9.8 times his height there, which is 8. Plus, let's see, kinetic energy at B. Well, that's 1/2 mv squared, right? And V is the thing we're looking for, right? All right? So that's the KE plus RKE. So remember, you guys, the RKE is the same as the KE. Oops.
2/5 as much in this case.
The same as, oh my glob. Same as the KE, but times
2/5.
the 2/5, because that's what our B is. Is everybody good up to there? All right, so next thing you do is think about what can be simplified. So your m's cancel out. All of the m's, not just some of the m's, cancel out. All right, and then let's see. So what do we got? 9.8 times 35 is 343. Equals 9.8 times 8 is what? 78.4, I think. Plus half of v squared is 0.5 v squared. 2/5 times 1/2. 2/5 is what? 0.4. Half of that would be 0.2. Cool? You guys are ominously quiet. Are we pretty cool? Okay, so look, we got 0.5 v squared plus 0.2 v squared. That's 0.7 v squared, right? So subtract the 78.4. Can we, and then algebra. And your v turns out to be, what is it, 19 point something or 16 point something?
19.4.
19.4? Is everybody cool getting from here to here? I hope. All right, so that's part A. Problems with it. Okay, so what are some of the things that people got tangled up on this one? I'm trying to figure out how we can help people, like front load things so that I'm not.
For me, it was just figuring out, like, the first part, like, figuring out what equals what.
Gotcha. Okay. Are you cool with how I came up with this big green expression up here about the GPE equaling? What else, you guys? Was some of it, yeah.
It was just like the whole height thing.
Oh, gotcha. G's the 27 instead of the 35? Gotcha. So that works if you want to do that, but then you need to make the height here 0.
And then what would be like negative height for the next part?
Exactly, yeah. All right, everybody good? Okay, cool. So we know the velocity here. It is 19.4 meters a second. All right, anything else before we go on to part B? Okay. So the trick with part B is how do I want to explain this? So as the ball flies through the air, by the time you get to the point down here, so at point C, here are the things we know. What's the GPE going to be at point C, you guys?
0.
0. Is everybody cool with that? All right. Now, as we went from point A to B, because it was rolling, what happens is it moves faster, but it also rolls faster, right? Like, doesn't that make sense? If you've got a thing that's rolling and speeding up, if it's moving faster, it's also got to be rolling faster, right? For your car to go faster, the wheels have to spin faster. Okay? But what happens is, from point B to point C, it's not rolling anymore, right? And so what happens is, is this crappy car going to work at all? No. I need to get a better white car. All right, well, we're going to use this. All right, so it's coming down the hill, speeding up, speeding up, speeding up, and then once it goes through the air, isn't the rate at which it spins going to stay constant? You guys see what I'm saying? All right, so what that means is the GP at point C is 0. The rotational kinetic energy at point C is equal to what?
Rotational kinetic energy at B.
It's the same as the rotational kinetic energy at point B, right?
And C is going to, and then just normal KE is going to increase.
And then exactly what Andrew said. And so your normal KE is going to increase, right? It's going to move faster linearly, but not angularly. Does that make sense or no? Okay, and the KE at C is something. We just don't know what. Follow? All right. And all of this has to add up to be the same as the total energy at any of the other points, because they're all the same, right? Does that make sense? All right, so what do you think would be a good thing to do? We already know the total energy at points A, B, and C. It's 343, right? Well, 343 M, I guess. So, yeah,
Then have the RKEs.
I think we need to find that RKE, don't we?
No. K's cancel out. I ignore for B and C.
Oh, I see. If you set B equal to C, that works. Yeah, I don't know. I mean, I guess there's a few different ways of doing that. That actually is not a bad idea. You're saying that. Is it going to let me do this? No. You're saying. Oh, where did it go? Did I erase?
Yeah.
Well, that was dumb. Why did I do that? Why didn't you guys tell me not to do that? I'm mad at you guys. All right. Yeah. So what Michael is saying is at this point, we have an expression for our KE, our GPE, and our RKE, right? And down here, it's going to be the same RKE, so those cancel. I don't know. What's more intuitive to you guys? Would you guys think to cancel them? You guys want to do it that way? Okay, cool. Well, let's do that then. So, all right. So rewinding then. So here is what we know. So total energy at point B is equal to total energy at point C. So the total energy at B was M times 9.8 times 8 plus 1/2 M times the velocity squared, which is 19.4. Right? Follow? Plus the RKE, right? At B, I guess. Equals, let's see, when we get to point C, our GPE is 0. There's going to be some KE, and we've still got that same RKE we had at B. And so what Michael is saying is that those RKEs cancel out, so you don't even need to worry about them. That's slick. Actually, I hadn't thought to do it that way. It's easier than what I had in mind. Does that make sense, you guys? Okay. The way I was thinking of doing it was actually calculating that RKE and then just subtracting it from the total energy, but this works too. Okay, everybody good? All right, so let's see, our M's cancel out, and then solve it, right? So we get, let's see, 78.4 plus whatever half of 19.4 squared is. I'm just writing the exact same thing again. And then do your algebra. And you get, what did I say was 23.1? Is that right? Follow you guys? All right. Problems of 13. We good? Yeah.
So answer keys, different.
Yeah, it's another reminder about that day. Yeah, I know, I'm sorry. Yeah. Sorry if that messed you up. And if you're not on my remind, join it. All right, so everybody good?
What?
Okay.